Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Veronica McGregor. We are just one day away from our InSight spacecraft meeting the atmosphere of Mars to begin the event that we call Entry, Descent, and Landing, or EDL. It's a nail-biting 6.5 minutes where numerous things have to take place perfectly in order for us to go from thousands of miles an hour to a gentle, safe landing speed. Our speakers today are going to describe everything that must go right during those minutes. They're also going to talk about how we'll be getting our communications back from InSight down to Earth so we know the progress of the spacecraft. And we're going to talk a little bit about the science that will be the reward from this mission getting to Mars. Now, before we get to our speakers, I just want to tell everybody right now to please bookmark a couple websites so that you can come back and join us tomorrow during the landing event. You can go to go.nasa.gov/Insight Toolkit to get a list of every platform where we will be streaming the commentary live. We will begin commentary at 11 a.m. Pacific Time, 2 p.m. Eastern Time. That will give you many ways that you can enjoy multiple streams of full commentary, clean feeds, and even a 360-degree broadcast from inside Mission Control, so you can feel like you're in there with the rest of the team. And also, nasa.gov/live, that's an even simpler URL to remember. All of our programming is always broadcast to that website. Now, following our speaker presentations today, we are going to take questions from the audience here. We have media, and we also have social media followers here today. Thank you so much for joining us. If you are calling in on the phone line, please remember to hit *1, and that will put you in the queue for questions. If you are joining us on social media, you can send us a question by using #AskNASA, and we'll be going to those questions later in the broadcast. And for now, I'm going to introduce our first speaker today. It is Thomas Zurbuchen. He is the NASA Associate Administrator for the Science Mission Directorate. Welcome.
Hey, thanks. What an exciting day. I mean, I almost can't wait. I'm really excited to go land this thing. But as we do this, of course, I stand back, and as the lead of NASA's Science Mission Directorate, I think of the risk and reward that is part of every one of these missions. To go to space always carries risks. We don't go take that risk because we're risk junkies and jump off airplanes. Some of us do, but most of us don't. We take the risk because it takes that risk to have that reward. The reward that has opened our understanding of worlds near and far, the reward that has transformed not only how we think about nature, but has really opened up the world in which we live and think in. And so whenever we look at that risk, kind of Mars stands tall in that risk distribution. And to talk about Mars, we recognize that we never take Mars for granted. Mars is hard. And so on the first chart here are the landers and rovers that we've landed here out of NASA. You see the ones, you recognize many of them. And of course, they're all the landers that humanity and rovers that humanity has ever landed successfully on Mars. Each one of them with the same kind of sweat and worry that I have right now in my stomach area. And of course, there's the one there at the bottom, we hope, of course, will increase our likelihood, our batting average, to you, Jeff, on Mars landers and rovers. Now, when I think about this, it's important to look at this in the context of all missions that we see on the second chart. All missions, you don't really have to look at any one of those, but you see all these names. That's all the missions that have ever been sent to Mars, orbiters, landers, and rovers, and these are the ones that were successful. Less than half of the words that were there at the beginning are now there. So we're, of course, worried. And what I asked myself, did we do everything that we could to support the team? And having met the team and being with the team, the answer to that is yes, and we're pulling for the team. Right now, for me, the hardest thing is to sit on my hands because there's nothing I can do to make the team more successful other than standing there and hoping and praying that everything is going to be just fine because they're doing exactly what they're supposed to do. And I'm just so excited to be part of that team, and hopefully, as we go through these 7 minutes of terror, kind of increasing the likelihood of humanity to actually land on Mars with this amazing vehicle that is out there ready to land that will, again, transform our knowledge of this amazing planet that's right next to us. And to introduce us to this mission, I'm happy to welcome now Tom Hoffman on stage, the project manager of InSight. Tom, take it away.
Thank you so much, Thomas. So as many people have, for Thanksgiving you have your family around, and luckily I was fortunate enough to have my 3 grandsons around, Connor, Declan, and Evan. And boy, when they get excited, they run around like crazy men, raising their hands, yelling, screaming, carrying on. And I have to tell you, inside of me right now, I'm just about that same way. I'm going to control myself as well as I can until we get a first notification of successful landing. But just to warn anybody who's sitting near me after that, I'm going to unleash my inner 4-year-old on you, so be careful. So as Thomas said, though, landing on Mars is never a foregone conclusion, and less than half of the times we've tried to either get into orbit or land on Mars, we have not been successful. So you might ask yourself, why is that? We've tried a lot. Why is it just not simple, easy thing that we can do every day? So if we go to the first graphic, I can give you a little bit of explanation of that. So on the Earth, we have a very large gravitational field, but we have a thick atmosphere that's very big. So we can actually dissipate the energy for entry vehicles pretty easily with that thick atmosphere, and usually can get a good soft landing, usually in the ocean, for Apollo at least. The Moon, on the other hand, doesn't have much of a gravitational pull, and it has no atmosphere. So that makes it a little bit easier as well to land on the Moon using propulsive technology. Mars is basically the worst of both worlds. We have an atmosphere that's about 1% of the Earth's atmosphere, and yet we have a gravitational field that's about 1/3 of the pull of Earth. And so what that means is we have very little energy in the atmosphere that we can dissipate. As we enter the atmosphere, we have very little ability to slow down until we get to the surface. So it makes it very challenging for us to land on Mars. And that's one of the main reasons why it is very challenging. We've done everything we can. We've done everything we can think of to make sure that we're going to be successful tomorrow, but you just never know what's going to happen. But let's explain a little bit about what is going to happen tomorrow. But first, we launched in May 5th of this year from Vandenberg Air Force Base, the very first time we've launched interplanetary mission from California. Very exciting, not very visible, but still a very exciting event. Since then, we've been doing a series of checkouts of the engineering and the science instruments to make sure that we're fully ready once we go through EDL and once we get to the surface and start the science. Everything's ready to go. All those checkouts have gone very well. We've also been doing things called trajectory correction maneuvers, or TCMs. And what those are designed to do is first get us pointed at Mars. The first couple ones that we did pointed us directly at Mars. We weren't pointed there when we launched. After that, the last couple have been designed to get us to a very specific point in the upper atmosphere that will get us to a very specific point on the ground. So let's run the video and we can see what we've been doing since we landed. So here is our target area, right here. This is where we want to land, at Elysium Planitia. After our TCM number 5, we were right here. You can see what the date is here. Sorry, this is after TCM 4. You can see what the date is here. And I'm not going to, don't run it yet, but when it starts running, what you'll see is this ellipse. This is our landing ellipse. It's going to start moving around just a little bit. What that is the DSN is tracking us. We're getting very good information about where we're going to land. So it moves around just a little bit as our knowledge improves. After we do the TCM, on November 18th, you'll see that we suddenly leap up here very close to where we want to be with our target. What's going to happen is then it's going to start moving around a little bit more. Again, as we've gotten more tracking data, we know that we're getting closer and closer to target. So let's go ahead and run that, and that's what you're going to see. So you can see it's moving around just a little bit. Our knowledge is getting better. It's not really the spacecraft changing. It's just our knowledge getting better. So after TCM5, we ended up here, which is not quite exactly on the red X. We're about 11 miles away. We moved 109 miles with that TCM5. We're still about 11 miles away. So just this morning, we had a decision meeting whether we were going to perform our last trajectory correction maneuver or not. And we decided at 6 a.m. that yes, indeed, we're going to do it. We want to avoid the area up here. That's not a great area to land. So we want to move down to this target. So we're going to be performing that a few hours from now, and hopefully within a few hours after that, we're going to know exactly where we're landing again. So things should be in good shape. So when we actually get there, after completing the TCM, we will be looking exactly like this. This is what our spacecraft looks like today. We have the cruise stage here, and the aeroshell is on this side. We're going to be in this configuration until about 7 minutes before we enter the atmosphere. At that point, we'll say goodbye to the cruise stage. We'll say thank you for getting us a nice ride to Mars. You're on your own now. This will go into the Mars atmosphere and burn up. And then we will be left with just the aeroshell. So inside of this aeroshell is our lander that's tucked in there very safely. We have a heat shield on this side. As we enter the atmosphere, that heat shield is going to dissipate about 90% of the energy that we have as it enters the atmosphere, eventually slowing us down to about 850 miles an hour, at which point we'll pop a parachute. That parachute will then slow us about 90% of the remaining energy down, and then we will get to the point where the lander takes over. So let's go ahead and run the video, and we can show that a little clearer. So there's our cruise stage. Goodbye, cruise stage. You're on your own. The rest of the aeroshell starts to enter the atmosphere. It heats up to about 3,000 degrees Fahrenheit in certain areas on that heat shield. That's going to dissipate a fair amount of the energy, getting us to the point where we feel comfortable popping the parachute. But we're still doing that at a supersonic speed. And so that is a very exciting moment for us to make sure that we get that parachute out. As we descend further, we'll let go of that heat shield. You can now see the lander inside of there. The legs will deploy. We'll start collecting radar data using an F-16-like radar to figure out what our altitude and our relative velocity is. We'll free fall for just a little bit, which is absolutely terrifying thought for me. But I've been told our descent thrusters will then start firing perfectly well, slowing us down to about 5 miles an hour once we finally get to the surface of Mars. So within about 6.5 minutes, we've gone from 12,300 miles an hour as we enter the atmosphere to just 5 miles an hour as we land safely on the surface of Mars. And where we're going to land is a place called Elysium Planitia, which very roughly translated means heavenly plain. And indeed, it is a very heavenly plain, and it is very plain. But it is actually perfect. It's safe. It's a great place not only to land, it's a great place to do the science that we want to do. So when we first land, we're going to get a picture back, hopefully right away. It's probably not going to be a very good picture, so don't get your expectations up too high. And there'll be a little bit of the picture that's actually missing. The reason is we have a dust cover, and that dust cover is going to be absorbing a lot of the dust that gets kicked up from the landing event. And then with our overflight of Marco and MRO, we're only going to get a part of that image. Eventually, though, we're going to get an image that looks something like this. Not the most exciting place to be. But, again, it's a very safe place. And in fact, I'm very hopeful that we have even less rocks. It's even more sandy and even more, dare I say, boring. Okay? But indeed, that's what I'm hoping for. But before we get there, we have to go through our entry, descent, and landing. And so we do that up in the mission support area. And I have a friend of mine up in the mission support area, Julie Wirtz-Chen, who is up there now. Hopefully she can come on. Julie, are you there?
I'm here, Tom.
Okay, great. You're in a very historic place. Can you tell us a little bit about where you are?
Sure. This is the Critical Events Mission Support Area. It was originally built in around 2000 in order for teams to come together to watch critical events. We first used the room in 2001 for the orbit insertion for Mars Odyssey, and we've used it to watch all critical or major events for every Outer Planets mission that JPL has flown since then. You might very well recognize this room from the MER landings, Mars Exploration Rovers, Spirit and Opportunity, or from Deep Impact's Comet Encounter, or from the last successful landing on Mars, Curiosity, 6 years ago, or of course the very emotional Cassini grand finale just last year. This room has been the backdrop to numerous really exciting events in planetary exploration history, and we're really excited to add to that list with InSight's landing on Mars tomorrow.
Oh, that's great. Can you tell me a little bit about what the people will be doing in their landing day tomorrow?
Yeah, so the very back row will have some NASA management and some project management. So Tom, yourself, and Bruce and Thomas will all be in that back row. Up here in this row will be more of the project people. So on the very far end of this row will be the navigators. They're the ones who have told us how to get to exactly where we are right now. Next to them along this row will be a subset of the Entry, Descent, and Landing Systems Engineering team. We're the folks who have really focused in on this phase of the mission, have really spent years getting all the details of these couple of minutes just right. And then as you come up here are more of the people who are going to be focusing on communication during landing. So radio science people will be right there. They're the ones who are eavesdropping in on our signal from all the way back here on Earth, trying to tell us some very basic state information from all the way back here. The Marco engineers, the CubeSats, will be over there. And they'll, of course, be trying to relay our very detailed InSight telemetry to us. And then right in the middle of everybody right here is Sandy Krasner. He's someone to keep an eye on tomorrow because he's our EDL communications engineer. And he'll really be the one who's coordinating everything to try and get that data from the lander up to the orbiters, back here to Earth, and onto these wonderful workstations.
Oh, that's cool. Now, since it's just you and me talking right now, can you maybe give me a sneak preview of some of the data displays that you're going to be looking at tomorrow?
Sure, just between you and me, no problem. We'll be looking at lots of different things. I think you're looking at a snapshot of one of the telemetry pages that we'll be looking at. You can see up in the left-hand side, we get short messages from the spacecraft that tell us where in the sequence we are of events. You can also see over on the right-hand side that there's a lot of data that just isn't even filled in yet. And that's because we haven't started the EDL sequence yet. So all of that will start filling in tomorrow when we start doing this. And of course, we'll be looking at lots of other pages too. We'll be looking at accelerations and velocities and thruster firings, and there'll be all sorts of good information.
Oh, that's cool. And I know you have a really, really cool special job on landing day. Can you describe that to everybody?
Sure. I'm extremely honored to be sitting up in the front row with Devin Kipp and Christine Soleil. And we'll be watching this telemetry real time, whatever we have, and trying to interpret it in real time. And Christine will be calling out events to let everybody know what's happening. So it should be fun.
That's great. I hope you guys have all brushed up on spacecraft.
That's right.
All right, that's fantastic. So as Julie mentioned, we have a lot of different ways that we're going to be getting information back from InSight during our entry, descent, and landing phase. The first and primary source is Mars Reconnaissance Orbiter. So it's going to be gathering all the data that we see from InSight as it goes through the entry, descent, and landing. But it's going to store that data, and it's not going to tell us what happened for about 3 hours, which is a little bit of delayed gratification, especially for me. I'm going to be very nervous. I want to know right now. We have another source, which is our UHF antenna that will be listened to directly on the Earth. We have 2 observatories, the Green Bank Observatory in West Virginia. We also have the Max Planck Observatory in Effelsberg, Germany. They'll be listening to see Doppler shifts. So we expect that we'll probably see the parachute deployment. We might see heat shield separation, and we'll definitely know that we've landed on the surface. Again, that's not a lot of information. We also have to wait about 5.5 hours to see that we finally got our solar arrays deployed, which is a key part of making sure that we're safely on the surface, ready to get our science back. We're not going to get that for about 5.5 hours from Odyssey. So all of that is lots of hours of delayed gratification. We do get an X-band beep from the spacecraft, though. That tells us that the spacecraft is arrived down on the surface. It says, it's taken me 7 months to get here. You've put me through 7 minutes of terror. But nonetheless, I'm safely on the surface. It's my safe call home. Everything's looking good so far. But that still happens before the solar arrays deploy. So because of all that delayed gratification, we decided that we'd bring a couple of stalkers with us called the Marco spacecraft. And what those spacecraft do is they'll be listening to us real time as we go through the entry, descent, and landing. They'll be looking at our UHF signal and immediately turning it around and sending an X-band signal down to the Earth. So if we run an animation, I can show you exactly how that works. So you can see in the middle is InSight. On each side are the 2 Marcos, Marco A and B. In the horizon, Mars Reconnaissance Orbiter, or MRO. is rising. So all of those are listening to the spacecraft, getting exactly the same data. But again, the Marcos should be sending us direct information back. They are a technology demonstration, so it's no guarantee that they're going to work on landing day. They've been working great so far, so we expect that they will, but you just never know what's going to happen. As the entry, descent, and landing goes through, that information goes to both MRO and the Marcos. Hopefully we get information from both of those, and Julie will be interpreting whatever information we get, along with Sandy and the rest of the people in the mission support area, making sure that we get that information out. But to tell you a little bit more about how Marco works, it's a really cool technology demonstration. I have Brian Clement, who's one of the systems engineers that worked on Marco. So Brian? Thank you.
Yeah, so I'll be here to tell you a little bit about Marco. Marco consists of 2 spacecraft. It's a technology demonstration mission, as Tom mentioned. And Marco consists of 2 CubeSats. And this is a scale model of Marco. 1 inch equals 1 inch here. So it's really a compact mission, overall very efficient. It's got 3 primary technology demonstration pieces that allow us to go where no small spacecraft has gone before. That is into deep space, interplanetary space. And those 3 pieces are a miniaturized radio that sits inside Marco here. It's about the size of a softball that allows us to communicate from almost 100 million miles away. The second piece is this beautiful HGA, or high gain antenna, that sits up here. This is called a reflect array antenna, and it allows us to focus that beam back towards Earth from this little feed right here. So this is how we are going to talk to Earth on that X-band while we're listening to InSight's entry, descent, and landing data. Now, as I said, this is a technology demonstration mission. We've proven all of these pieces up so far during our transit towards Mars. The last piece is the cold gas propulsion unit. Now, you may have heard about this. This uses fire extinguisher propellant as its means of locomotion, and it allows us to navigate and maneuver in deep space. As Tom was saying, you have to go through TCMs, trajectory control maneuvers. This is how we do it on Marco with fire extinguisher propellant to allow us to move slowly towards our goal throughout the mission. Now, we have an animation that'll show a little bit about how the communication occurs, but the most important piece here for tomorrow's event is the UHF antenna down here. So if we could roll that animation, we'll talk a little bit about how that works. As InSight approaches Mars, we'll be then picking up communication using that antenna at the bottom of Marco. InSight will be broadcasting a UHF signal, and then the Marcos will repeat that signal, but in the X-band, looking at Earth very closely with that HGA that we have on top there. This is how we are going to allow Marco to relay data back to Earth rapidly and understand what's gone on with EDL if everything goes to plan. Now, of course, the 2 Marco missions being a technology demonstration mission, we don't need to perform that relay for InSight to be successful. However, we believe that this is a really interesting technology overall, and we've really shown something unique in deep space that will allow us to further future missions in a compact and efficient way. And finally, I wanted to show you a little bit about the cameras on Marco. So we have a camera right here. You may have seen pictures. And we've been learning how to take pictures as we've been going along. And when we originally left on May 5th, a few days later, we took a picture of Earth. You saw a pale blue dot in that picture. And as we've been approaching Mars, we've been taking pictures as well. If we could put one of those up. What we have here is the high gain antenna, which you see up here. And right down here in this lower left quadrant is Mars on the approach. So we're really looking forward to getting in closer and closer and closer to Mars over the next 24 hours and performing the entry, descent, and landing relay for InSight. And so that's Marco in a nutshell, a small compact mission that's going to allow us to do some really unique things. But back to InSight, we have the principal investigator here, Bruce Banner, to describe some of the science behind InSight.
Okay, so you've been hearing a lot about the risks involved in landing tomorrow and all the intricate dance that the spacecraft has to go through in order to get down to the surface. And I'm very cognizant of all that stuff. I've been living that design for the last 7 years. But what I'm here to talk to you today about is the payoff. Okay, this is the benefit. This is what we're going to Mars for. So we've been doing the design, construction of the spacecraft, the operation for about 7 years. We've been in space about a little less than 7 months. It's going to take us a little less than 7 minutes to get down to the surface, and then we're going to be down on the surface, and that's when the mission actually starts. So everything up to now has just been a prologue. It actually starts tomorrow. Feels like it's a climax, but it's actually the beginning. And so tomorrow, we're going to be down on the surface in Elysium Planitia. And for those of you who are up on your Martian geology and geography, we're going to be right about here, okay, on the surface of Mars. But what we're going to be looking at is not the area around here. What we're going to be looking at is this, the deep interior of Mars, looking at the deep core of Mars, its mantle, and its thin crust up here that have all the rocks that we actually have access to. That is the goal of the InSight mission, is to actually map out the inside of Mars in 3 dimensions so that we understand the inside of Mars as well as we have come to understand the surface of Mars. And by doing that, we're not only just sort of exploring Mars itself, but we're actually going back in time, back 4.5 billion years to the sort of the origin of the solar system. The structure of Mars, this crust, mantle, and core, which keeps on swinging out of sight, this crust, mantle, and core was set up in the first few tens of millions of years after Mars was formed. Probably maybe even 20 million years. And that's out of 4.5 billion years, that's just a really tiny slice of time. The Earth was also formed at about the same time. It formed a crust, mantle, and core, as Mars did. But after that, Earth just kept on going. It says, hey, this is fun. I'm going on. I'm going to do plate tectonics. I'm going to do mantle convection. I'm going to stir everything up. And then you get 4.5 billion years and later go, oh, wait a second. All that evidence has been erased. And so anybody who comes along and wants to know where we came from, you're tough luck. Luckily, we can go to Mars, and Mars decided to rest on its laurels after it formed. And so when we look at the crust of Mars, that's a snapshot into the past of what the crust of the Earth might have looked like 4.5 billion years ago before it got all busy. So in order to understand the formation of the Earth, the way that the Earth evolved into a planet which is habitable, which has oceans, which has an atmosphere, which has a nice temperature. If you're not in New York right now, at least it's a nice temperature, and whereas other planets did not go that way. And they're the very details, the small little details of that evolution, is what we think makes the difference between having a nice planet like the Earth, a place where you can take a vacation and get a tan, or a place like Venus where you're going to burn up in a matter of seconds, or Mars where you probably freeze to death and wouldn't be able to breathe very well. Those details are pretty important in terms of living, but they're very small details in terms of the way the planet evolved. And we're trying to get a good enough, precise enough measurement of the conditions of early Mars that we can refine our models and understand how those details send us down different paths. Okay, so how are we going to do that? We're going to do that with a couple of geophysical techniques. That's using physics to study geological processes. And the first one, and the most important one, is seismology. Seismology is the study of earthquakes, or in our case, Marsquakes. And it's not just studying the quakes themselves, but we're using the waves generated by those quakes, the vibrational waves which pass through the planet, in order to probe deep down into the planet. When we look at things with our eyeballs, we're using light waves which bounce off of things. They travel through the atmosphere, they travel through glass, they get bent, they get reflected, and our eyes kind of puts together all that information to give us three-dimensional knowledge of the world around us. Okay, so when we turn our eyes downwards to look at the core of the planet, it doesn't work so well because light waves don't go through rocks. But the waves that do go through rocks are seismic waves. And so on Mars, when there's a Marsquake, where the crust moves suddenly, starts vibrations moving through the planet, it's like a flashbulb going off in the seismic world. And our seismometer is our eyes on Mars, which take those waves and let us turn those waves into a 3D picture of the inside of Mars. And so let's run the first animation here. This is where a Mars quake has occurred on Mars. These are surface waves traveling across the surface. As they go past the seismometer, here's the seismogram that's generated. The nice thing about Mars is it's small enough that those surface waves keep going around the Mars. They go to the other side. They pass each other at what we call the antipode, the opposite side of the planet, and they keep on coming back around. As they come back around, they pass the spacecraft again. The seismometer picks up the seismic waves that have gone around, and they pick up the one that's gone around the other way as well. And so you may have heard that it takes 3 seismometers to locate an earthquake and do seismology. Well, we only have 1 seismometer, but we're using extra information. Here we have the P wave, the S wave, and the surface wave, but we have these extra 2 surface wave events that go around the planet because Mars is small. It doesn't absorb the waves as quickly as the Earth does. And we can use this extra information to actually locate how far away that Mars quake was from our spacecraft. We can use some other analysis to figure out which way those waves are coming from, figure out where that Mars quake is, and with that information, we can use the information from the velocities of the waves to probe inside the planet, figure out what it's made out of, and where the boundaries are. So in order to do that, we use an instrument called the seismometer. And I have a couple of seismometers here. Well, I have 1 seismometer and 1 fake seismometer. This is Streckheisen STS-2. It's a so-called portable seismometer. It's used quite a bit in geology. It's very similar in size to this, which is a 3D printed model of our InSight seismometer. On the Earth, this is a portable seismometer, which means we ship it in a crate that's about this big, full of foam so that it doesn't get broken. When we take it out in the field, we don't just set it down on the ground. We usually dig a hole, put down a concrete slab, put insulation around it and everything so that the temperature is nice and uniform. And so then we can use this seismometer to do the kind of seismology that I'm talking about on Mars. On Mars, we have this guy. This is the heart of our whole mission. Inside this are 3 seismic sensors, and it has to do the same kinds of things this does, but we don't have someone there to dig a deep hole, put insulation around, and so forth. And these seismometers are so sensitive, they're picking up vibrations from these quakes. These are not the kinds of vibrations that knock your house down. These are very tiny vibrations that have traveled through the entire planet. And the sensitivity of these seismometers is such that they can see vibrations with an amplitude of about the size of an atom, maybe a fraction of an atom. And so you can imagine that if there's a little bit of wind blowing, if there's the temperature goes up and down a little bit, things expand and contract, all those things are going to go and show up in our signal. And so if I can have the next picture, this is what we do in order to make that work. Okay, so right here, this yellow part in the very center is that, what we call our sphere. It's not really a sphere, but it's close enough. You can see some of the stuff inside it. What we've done is, first of all, we've evacuated that sphere. It's a vacuum, a hard vacuum inside. That helps to insulate it. Then we put sort of another vacuum bottle around it. This is our thermal enclosure. It has a hollow inside. This protects it from the temperature variations on Mars, which can be as much as 100 degrees as you go from day to night. And finally, we put this dome over the top. We call it our wind and thermal shield. That protects it from the wind and protects it a little bit more from the temperature. It's actually kind of cool. It has a hard dome, and then it has kind of an accordion thermal blanket down here. And then we actually have chainmail at the bottom that actually can conform itself to the irregular ground, keep the wind from going underneath it. And so by putting all these different layers of insulation between our seismic sensors and the environment, we actually have what we call a thermal time constant of about 7.5 or 8 hours it takes for a thermal variation to go from the outside to the inside, and that keeps it going. Okay, so this is what we're going to do on Mars. I think that's about all I have to say. I think we can wrap it up and go back to Veronica.
All right, thank you. We're going to invite, stay where you are. We're going to invite all the speakers to come back on stage, and we're going to open it up to questions. We're going to take questions from here in the auditorium. We'll also be going to questions on the phone line. If you're on the phone line, please hit *1 to get into the queue so we know you're there waiting with a question. We're also going to take questions from social media online using the hashtag AskNASA. All right, let's start here in the auditorium. I'm going to start on this side with Emily Lakdawala.
Emily Lakdawala with the Planetary Society. I have a couple of Marco questions. I'm wondering if you can give some details on flyby distances for Mars. Are they basically on the course that you planned for them? What will the range be to InSight during landing? And you showed us a cool picture. Are you planning to take any more as you approach Mars?
Okay, you may have to remind me of some of those questions as we go through. So first of all, the flyby will be about 2,500 miles above the surface of Mars. The distance to InSight directly as it lands will be approximately 3,000 to 3,500. And then I think your other question was pictures. Yes, we are taking more pictures. We'll see how we do with those. And the Marco use a very off-the-shelf camera, if you will. And so we're learning as we go with those pictures. So every time we take one is a little bit more information. We've been happy so far, but we'll see how we do as we get closer.
Thank you.
All right, we're going to go one in front here to Steve Futterman. Go ahead.
Steve Futterman from CBS News. For Tom, I want to sort of get to your psychological makeup right now. What is your mood right now? Are you nervous, excited, a bit of both? And what is it going to be like during these 7 minutes of terror?
Yeah, that's a great question. I am completely excited and completely nervous all at the same time because everything that we've done to date makes us feel comfortable and confident we're going to land on Mars, but everything has to go perfectly, and Mars could always throw us a curveball, to use the baseball analogy, that may decrease our batting average. But I think we've been practicing very well. I'm confident, but very trepidatious. I have not been sleeping that great. Might be because I have 2- and 4-year-old kids running around the house all the time. But nonetheless, I'm going to be very excited once we get that first signal back that shows that we've successfully landed on Mars. I am totally going to unleash my inner 4-year-old at that point.
Okay, I'm going to go to the phone lines next. We have AP on the phone. Please go ahead with your question.
Marcia, your line is open.
Yes, hi. We've heard that Dr. Zurbuchen's got some stomach stuff going on from nerves, and we've got the inner 4-year-old going to be unleashed by Tom Hoffman. Dr. Bannert, I'd like to get a look into your mind and stomach right now. I mean, how are you feeling, and how do you anticipate you're going to be dealing with the critical times tomorrow before touchdowns?
Well, I have to admit I'm getting a little nervous. I wasn't sure whether, actually, I'm probably more nervous about this press briefing than I am about the landing. But it'll get there. It'll get there. I've been really, along with Tom and a lot of other people, been living this mission for about 6 years. And we've been thinking of everything that could possibly go wrong, which is something that gives you pause sometimes, because there's a lot of things that can go wrong. But every time you think of something go wrong, you figure out how to mitigate it, how to either make it less likely or how to fix it. And so we've fixed an incredible number of things over the last 6 years. And I'm actually really confident that personally that we're going to land safely tomorrow. Doesn't mean I'm not nervous, but we'll see when they call safe touchdown. We'll see just how nervous I actually was. I'll find out with the rest of you, I think.
Hey, Bruce, I know you've been working for the last 6 years really hard on this mission, but you should tell them how long you've been dreaming of this mission.
Oh, well, I was actually here at JPL in 1976 when Viking landed on Mars. I was a geophysical graduate student and was really disappointed when the seismometers on Viking didn't work out. And I thought back then, boy, we really need to send a seismometer back to Mars. And then I went back to whatever it was I was working on. And then about 10 years later, in the late 80s, I started working with some engineers at JPL on seismometers and kind of got the mission bug. I kind of caught the mission bug and got a more or less some people say obsessed about sending a mission to Mars. So I've really been working pretty steadily for 25 to 30 years on this, and have had about 6 or 8 unsuccessful proposals before this one, but which each one is a learning experience, and so I'd say I'm a patient person. As well as persistent, but yeah, it's been a long time. This is really a long time dream come true for me.
Yeah. Okay, we're going to go to one more question on the phone line. Irish TV, Leo Enright, go ahead, please.
Thanks very much, Veronica. And there are lots of 4-year-olds with good Celtic names watching this as well. My question is to do really with the European involvement. And I just wondered, I cannot remember, and as Veronica knows, I've covered this for a long time, I cannot remember any interplanetary mission that has this level of international cooperation. I just wondered, am I right about that? Is this unique in modern history, or have I missed something?
So why don't I talk about this? It's Thomas Zurbuchen. So close to 2/3 of our missions do have international involvement. What's unique about this one, if you take the whole payload, which of course is the why of a mission, right? It's there. Of course, the piece in front of you, I met the guy in France. I remember I was introduced to him by the CEO of the company and says, this is the guy. I still remember him, tattoos down his arms. He has the magic touch. He's the only one who really knows how to put these super sensitive sensors into the sphere. And so I met him, like I'm grateful to him, right? Together with his colleagues there at Southern and elsewhere in CNES. Of course, the other instrument that you didn't talk much about, but you can, of course, from Germany. Of course, the electronics is from Switzerland. Over here is here from Germany. There's also Polish contributions, as well as others. And so kind of just as a fraction of payload, it is unique. It is unique in terms of just how much is being done elsewhere. Of course, we believe in the United States that leadership and collaboration are not contradicting values. We believe that the best is served for humanity if we actually have the best seismology instrument, the best thermal probe, and in this case, they're built elsewhere. And so that's why we're doing that. Bruce, what did I miss?
That's pretty much that pretty much covers it. I mean, all these instruments, for example, the seismometer is being supplied by the French Space Agency, but there have been substantial contributions from the United Kingdom, from Germany, from Switzerland, and from the United States. We had actually a pretty big part of that, and so it's really a collaboration, and the collaboration really doesn't have any respect for boundaries. We just get the best people, the best technology wherever we can find it.
Okay, we're going to take it back here in the room. We have a question here on the end. Go ahead.
Jeff Faust, Space News. For Tom, can you give us a little more details on this final TCM in terms of the timing and duration? And are you aiming to get right back onto that X in the center or some offset from it?
Yeah, so we're hoping that this afternoon we do just a very small burn. It's only a few centimeters per second. Which is it's just almost a breath of air out of your mouth. We hope that we're going to move about 11 miles from where we are today to that red X. We're a little bit to the northwest. If we go further northwest than where we're currently showing, we get into a region that we're not as comfortable landing in, which is the reason we had a very exciting, and it wasn't clear what the answer was going to be in our 6 o'clock meeting this morning. We listened to all the different inputs. And the final decision was to go ahead and do the TCM. Let's move ourselves back to that red X and be exactly where we really want to land for both safety standpoint as well as making sure that we have the right location for our science instruments.
Okay, we have a question in the back row. There you go.
Hi, Fred Bastien YouTube channel. I have a question about the insights we can get from InSight about the science over there. What's the main hypothesis, but mostly what's the craziest thing we could learn? What's the most mind-blowing thing we could learn about Mars through InSight?
Wow, I mean, I think my imagination's really always been challenged by Mars because we keep on running into things that are crazier than I ever imagined. I think, we've thought a lot about, how many quakes there might be on Mars or how active Mars can be. I think probably what's going to happen is we're going to find out that the whole question of sort of seismicity, which is the distribution and rate of seismicity on Mars, is going to tell us some things that we had absolutely no idea were going on in Mars. I mean, seismology is one of the ways that we really confirm plate tectonics on the Earth, looking at where all the earthquakes bunch along plate boundaries and allowed us to see where the plate boundaries were. On Mars, when we start getting these Mars quakes, they're going to be telling us, where there's stuff going on Mars, where the forces are concentrating. And I think that's going to tell us something that was probably completely absent from our models. But then again, now that I've thought of it, it's probably not true. So.
All right, again in the back row there.
Hi there. It's Ivan Semenek with the Globe and Mail. Just a short one about that safe call home. Can you just remind us precisely when you're expecting that to arrive, how we'll know that you've got it, and how you would spring into action or what scenarios you might pursue if you don't get it right away?
Yeah, so about 7 minutes after we land, we're expecting to get an X-band beep. If we don't get that X-band beep, all is not lost. That just means that we're in a slightly different mode. We would be in something called safe mode, which by its name you can figure out it's safe. In that mode, the only thing that we would really lose is that first image. Everything else is autonomously done by the spacecraft, so we'll get the solar arrays deployed, we'll get making sure that we're thermally and energy safe, and then we will start talking with the orbiting assets, Odyssey, Mars Reconnaissance Orbital. We'll start getting that data up to them. So it really, 7 minutes means everything's great. If we get it a little bit earlier or a little bit after that, it still means everything's in pretty good shape. We're just not going to get a picture back for a while.
Thanks.
Okay, I'm going to go here to Ian. There we go.
Hi, Ian O'Neill with Scientific American and HowStuffWorks.com. I had a question. In Mars' ancient past, it was hit by a massive impact. How will InSight expose the interior of Mars to explain what actually may have hit it, if it did happen, or perhaps some other explanation?
Okay, I assume you're talking about the origin of the dichotomy boundary in the northern plains, which are a different level and different character than the southern plains. And one thing InSight will be able to do is, we think if we have a reasonable number of Mars quakes that are distributed around the planet, we'll be able to look at waves that are coming at us from the north, through the northern plains, which are the putative location of this giant impact, and waves that are coming from the south, and use the crustal thickness that we can determine from both of those in order to see what the difference in the thickness of the crust is between the north and the south. And that will feed into evaluation of various different models of how the northern plains formed. And so I think that's probably our best bet for helping to constrain that particular problem.
Thank you.
Okay, next question. Go ahead.
Fig O'Reilly with Girls Who Code. My question is, how long do you expect it will take to generate enough usable data to produce insights about Mars's interior?
Okay, so InSight is, once we get to the surface, InSight is a slow motion mission. Okay, we take our time getting our instruments down. It'll probably take at least probably more like 3 months, maybe even longer, to get our instruments down. It's going to take us a month or so to get them all calibrated and tuned to Mars's conditions, and then we'll start collecting our data. We'll start collecting the data at the beginning, but then we'll start collecting the best, the cleanest data. I would say probably it's going to be at least 6 months before we even get a glimmer of what we're looking for. And a lot of the really basic questions, I think it's going to take close to the full two-year mission. We might be getting stuff out before that, but it really depends on how benevolent Mars is feeling. How many Mars quakes it throws at us. The more Mars quakes, the better. We just love that shaking, and so the more shaking it does, the better, we can see the inside. Let those flash bulbs keep on going off. If it's nice and a good clip, we'll maybe even earlier than that. But with the rate that we're expecting, we'll probably be getting some of those really basic results out probably not much earlier than 2 years in. A lot of other cool stuff will happen. We'll get weather reports every day. We'll be measuring the heat flow. We'll be measuring the wobble. So there'll certainly be a stream of results coming out. But in terms of the really deep questions, I think hold on to your hat for a while.
Okay, we only have time for a couple more questions. I'm going to go to social media, see if we've got any burning questions coming in from online.
So many questions, a very lively YouTube chat, and everybody out there on Twitter using Ask NASA, thank you so much. We will be answering more online after the broadcast is over. So we talked about inner 4-year-olds. We have a real 4-year-old, Ellie 4 and Jackson 8, together want to know how the information we learn from NASA InSight will shape future missions to Mars.
Yeah, so I think there's a couple parts of that question. There's certainly the science aspect. I can talk to the engineering aspect. One of the things that we do with every EDL mission, entry, descent, and landing, is we gather a lot of information that we're getting from the spacecraft as it goes through that process. Every single time we do that, we learn something a little bit different. We change what we're doing. We change the parameters the next time, maybe change a little bit of the design of that. So certainly we're going to learn a lot from that activity, and we'll feed that forward to future missions.
Yeah, and of course, the way we think about the future mission is Mars 2020 is even though everything this weekend, tomorrow is focused on InSight, there's other people here on this campus that are worrying about what's going to happen in 2020 when we're going back with a rover just as big as Curiosity and doing really the first leg of a sample return. And it's that very information that you just talked about, information that teaches us how to do safely these entry, descent, and landing, as well as other things about the atmosphere and the environment that will help us with that mission and many to come.
All right, and Bruce, a couple questions from Bill Tandy over on Twitter. So will the seismometer collect science as the heat flow probe is hammering into Mars? And what happens if that probe encounters a rock or ice as it descends?
We're definitely going to be listening to the vibrations that are going to be put out by that hammer of our heat flow probe. It's kind of a bonus experiment for us. It really is not connected to our main goal of looking at the deep interior. The waves from that hammer will probably penetrate, maybe 40 or 50 or possibly 100 feet down into the soil. So it'll give us information possibly about layering in the soil and the rocks right underneath our lander. And again, this is not something that we planned originally, but it's really kind of taken the imagination of the team, and a lot of people have been working on that and trying to figure out how to make that particular experiment work, because it's just so cool. It's just so fun. So as far as whether it encounters a rock, our mole is a pretty muscular mole. It can get around actually smaller rocks. Anything smaller than about 2 inches or so, it'll just push it aside. If it gets to a larger rock, it depends on the slope of the face. If it's a slanted face, the mole will actually work itself sideways and go around the rock. But if it hits a flat, large rock, that's just as far as it can go. And we've looked at the statistics of how many rocks we expect under the surface. That's gone into actually our choice of landing area of looking for a place with few rocks on the surface that we can extrapolate to few rocks under the surface. And so we feel like we have, from our calculations, a high probability of success of getting down at least 10 feet, which is deep enough to do our measurements easily, and probably to the full 16 feet that we're shooting for.
Veronica, do we have time for one more question?
We're using up time quickly.
Find us
here.
online.
Exactly. Not only will social media will continue to answer your questions online, but there's also another show coming up later on today at 1 p.m. Pacific, 4 p.m. Eastern Time. It is for all of our social media attendees today. It's another opportunity for a lot of great Q&A with the mission team members. So if you don't hear your question now, you might hear it in that show. I've got one more. Leo Enright, Irish TV, you've got a follow-up question on the phone line, and go ahead.
Oh, thank you very much indeed, Veronica. Appreciate it. I was just wondering about this TCM tonight. It's, I think, about midnight our time here in Europe. How important will the new Norcia ESA tracking station in Western Australia be? I know it's scheduled to be watching out, but has it suddenly gained an importance that it didn't have now that you have this burn?
Well, we've always appreciated the support that we've been getting from it, but we're actually not going to be using that for anything related to the trajectory correction maneuver coming up. We don't have really time to do much tracking after that trajectory correction maneuver this afternoon, and so we're going to do it, and we're going to be targeted where we want to go, and that's going to be kind of it.
Okay, for those of you in the room, you'll have an opportunity to come up and ask them some questions when we're off the air. I do want to wrap the broadcast at this time, so I want to thank all the speakers for being here today. Great information. Okay, and for all of you watching, a reminder that we land tomorrow. Our commentary begins at 2 a.m. Pacific time. I'm sorry, let me correct that. 11 a.m. Commentary begins at 11 a.m. Pacific time, 2 p.m. Eastern time. Landing takes place about an hour into the show there, maybe 50 minutes, so tune in. There's multiple ways to watch. You can go to nasa.gov/live. You can see the broadcast there. You can also check out our InSight toolkit because it gives you multiple options for watching the live stream. That is at go.nasa.gov/InSight toolkit. You'll learn where we will be feeding to YouTube, to Facebook, also our live 360-degree feed from inside Mission Control. There's also a tab on that site that says Watch in Person. Click there if you want to find out where there is an in-person viewing event that you can attend. There are events taking place from Los Angeles to New York, even in Times Square tomorrow. If you happen to be out in the cold, you can watch from multiple locations. We will be back, as I mentioned, at 1 p.m. Pacific time today with the NASA Social Show. And again, commentary tomorrow, 11 a.m. Pacific, 2 p.m. Eastern time. Thank you all for joining us today, and go InSight.